Okay, welcome to our last lecture on principal components analysis. I'm going to go through some examples and how to use this in practice, and a little bit more about how to understand what PCA actually is. So we ended up last time talking about the Pca theorem. And the Pca theorem essentially said that we can approximate data as by taking the mean. So for now we might just talk about zero mean data, and then having that be the sum, weighted sum of eigenvectors of the matrix, the correlation or the covariance matrix of X times X transpose. So let's break this down into in a little bit more practical terms. So we have two things going on here. One is, with PCA, we have this theorem that says we can approximate a value using some, breaking it down and using these eigenvectors as a basis and using just a certain number of eigenvectors. So that's step one. The other point of using PCA is to say, rather than approximate the value itself, why don't we just plain project it into another space that's a lower dimensional and use that to operate on. Now these two concepts aren't unrelated, but sometimes it can get a little bit confusing. So let me look at the second part here, where we are actually just projecting our value into a lower dimensional space. Okay, so that's what we have right here. Project data to lower dimension space. So Z actually could be full dimensional, and that's okay. But the fact is it's in a different space. It's in a projection space. And we are going to use our matrix W, and I'll talk about W in just a minute, and use that to project X, as you see. Now, we want, for the derivation and practical implementation of this, we want X to be zero mean. And so we will often have as a first step removing the mean of the data. Once we've done that, then everything can proceed as normal. It's important to know that anytime you have data that is not mean removed, well, just remove the mean and keep going. And then we make the assumption that we have zero mean data. Okay, so Z and X are column vectors. Z may actually be a degenerate column vector, meaning that it may actually be a scalar, only have one element in the column vector. And W is a matrix. And W may be degenerate in that it only has one column, making it a vector. But in general, W is a matrix, and Z and X, and also the mean vector, are all column vectors. Okay, so we want to project this into a lower dimensional data space, and if we had a lot of data, as we talked about last time, many xi vectors, we can put them in a matrix, denoted by capital X. And I'm going to put the tilde here. And from here on out, we will assume that we're dealing with zero mean data. Okay. So where we were last time was we defined Q is equal to X transpose is the sample covariance or data covariance matrix. I'm just going to write covariance. And the idea, or one idea behind principal components analysis, there's actually several ways of approaching this, but one idea is to say what we really want is for our projection W to spread the data out as much as possible. So if we are trying to do some classification, then presumably if we can spread the data out, it's going to be easier to see where the different classes are. And so the way that that happens is we have this covariance matrix right here, so that should be handy. The covariance matrix is going to tell us the variance of the data along different dimensions. And so what we would like to do is find that dimension along which the data is the most widely spread apart, and that's going to correspond to the eigenvalue, or the eigenvector having the largest eigenvalue. Okay, so the columns of W are the eigenvectors of Q sorted by eigenvalue, largest to smallest. Now, we could use all of the eigenvectors of Q, and since Q is symmetric and square, it's going to have all orthogonal eigenvectors. In other words, even if you have identical, repeated eigenvalues, the eigenvectors themselves will be and can be always found as an orthonormal set. So this is kind of nice. It means we can use W to actually just transform X into another space, but it'll all be there. What this also means is that, and for right now I'm going to introduce some new notation. I'm going to say let V be the matrix of all the eigenvectors of Q sorted as above. You might have noticed I just deleted the eigenvectors. The columns on the sentence prior, the columns of W are made up of eigenvectors, but not necessarily all of them. It's however many we choose. Okay, but V is the matrix of all of them. So what does that mean? Well, we have the properties of V. We know that V transpose is equal to I is equal to V transpose V. So the left and the right eigenvectors are all orthonormal. So this is a really handy little way to go. Why is that? Well, let's just assume right now that we wanted Z is equal to V transpose times x. And we wanted to get x back. Well, we can multiply on the left-hand side by v. So we would get vz is equal to v transpose x is equal to x, and that gives us our x back. So if we only use sum of the columns of x, columns of v, w, we have z is equal to w transpose x, but we can't, in general, get back x. What we get is x approximate, and I'm just going to say x approximately equals w times z, where once again w does not have all the columns. So this is the approximation that we talked about with the Pca theorem. Okay, in general, you would have to add back in the mean of x if you didn't have a zero mean x value to begin with. Okay, so let's put this into practice. I've got some code, some Matlab code that I've generated, and I've already run it to kind of speed things up. And I'll talk through it as we go. Okay, so we have 1,000 samples of two-dimensional data. And you can see them plotted over here in blue. So I first, as with the example last time, created random samples and then I skewed them. So they're kind of skewed. You can ignore the red for a minute. We'll get there. First thing we did was remove the mean. So removing the mean of this actually has very little effect, because the mean of x should be approximately 0, and the more samples we have, the closer to 0 it will get. And it turns out that the mean was very small, but there was a mean there, and that will show up. We'll run another example in a minute where you can see that. Next, we take the covariance matrix, which is Q as defined before. So Q is equal to, in this case, x times xm, or xm times xm, where xm is the mean removed data. And we find its eigenvectors in V and eigenvalues in this diagonal matrix D. Matlab doesn't always return the eigenvalues sorted, so we're going to first sort them in descending order, so largest first. They're going to be positive because A is a symmetric covariance matrix, so it'll always have at least non-negative eigenvalues. We're going to sort them, find the sort order, and then sort the eigenvalues and the corresponding eigenvectors. Turns out we're not going to be using the eigenvalues again. I just put it in there for completeness, the sorting of the eigenvalues. Next, we we want to form our approximation. So here we're going to define our W matrix. Our W matrix will be a projection matrix that we're going to use to approximate our data samples. And so P in this example is equal to 1. If P is equal to 2, since we started with two-dimensional data, we should have a perfect approximation of the data. But if P is equal to 1, and we're only using one eigenvector to approximate the data, and it turns out we use the one, as discussed before, in the direction of the largest variance in the data. So here it is right here. Get lower dimensional data approximation. So use this for your machine learning algorithm or classification or whatever you may have where you want to operate on lower data. So G is the main thing that you want to use. Everything else that we're doing from this point on is just kind of illustrating how this works and the effect on the data. But that's it. That's what you want. Okay, so we talked about getting the data back, our approximation, and getting that approximation back. I'm sorry, I switched notation here, and I probably shouldn't have. In the slides on the previous page, I used Z right here, and the W is, or X, the approximate value of X is W times Z plus mu X, and here in my code I used G. So G is now our lower dimensional approximation. And back into the full dimension, we have X approximately equals W times G plus the mean vector. And what I've plotted over here on the right is exactly that. So we have the original data is blue, and our approximation is in red. Okay, so it's a pretty good approximation of the data. Kind of gets rid of the noise and goes in the right dimension there. So now what happens in practice is that you'll have training data, you'll have examples to work from, and you will find the PCA, you'll put that into a lower dimension, and now someone comes along and brings a new sample. What do you do with your new sample? How do you get it into the same lower dimension? Well, that's this part right here. We're given some new data, and this is why my notation's a little messed up, because I use Z here for the new data instead of the approximation as I did on the previous page. I apologize for that. So here we have 20 new samples, and this part right here is just creating the new samples the same way we did before. As before, we need to remove the mean, but when we remove the mean, we're using the previous mean. Why is that? Well, in practice, if you had 100,000 new samples, you could remove the mean of those 100,000 new samples, and that would be fine. But if we just have 20 samples, the mean is likely to be very noisy. So we're going to use the mean, assuming they came from the same distribution that we calculated on our training data. Now, we're just about done. Project data into lower dimension. using our previously obtained W matrix. There. Now we have our lower dimensional approximation. I've gone ahead and projected that approximation back into our original space, as we did before in the next line, and plotted it over here on the right. So let's look at what's going on here on the right. We can see that these samples are all brought down to the line, to the closest spot on that line. That it's just a straight projection onto that space spanned by our single W vector that we had there. Okay, that's about it. I'm going to show you what happens in Matlab here when we approximate this using the full p equals 2. So we're using W is now equal to the full V matrix, eigenvalue or eigenvector matrix. And so let's zoom in some point right here, and we see that no matter how close you get, the red and the blue being the original and the red being our approximation, overlay each other perfectly. And the same goes for figure 2 here, where we're dealing with our new data samples. So I did PCA in this example using just the basic analysis commands that I've shown you. The only thing I used canned routines for was the finding the eigenvalues and eigenvectors. But you can also do, let's see, doc PCA. Matlab also has a PCA routine built right in, and there are actually several other options that you can do with the Matlab routine, but it's documented here. I personally, when especially learning something new, prefer to do it from first principles so I know what's going on, and then migrate over to the built-in commands. But if you just need to do this as a quick and dirty data analysis, using the PCA command is often a good way to go. Okay, thank you.